We're given the function sine of x over x, and then we're asked to figure some stuff out when x equals 0. Well, x can't equal 0, right? It can't, because when it does, the denominator is 0, and then that makes the whole thing undefined. So the question that the textbook is really asking us is to give a formula for the extended function that is continuous at this point. So we've got to kind of define if it's possible to make this function continuous. So let's graph it. I love to graph the functions and look at the behavior and see what's going on, because that gives me an idea of how I might approach it. Now, most of the time when you have something in the denominator that has x, you have a vertical asymptote, because nowhere can x equal 0. The key here is if it's pluggable or not is based upon it's really based upon what the limits are, the two-sided limits as we approach 0. Okay? So I think I've graphed this properly. If I think about the behavior of sine, sine is an oscillating or sinusogenous function. It oscillates between +1 and -1. It has a period of 2 pi. Now, if I put x on the bottom as x approaches infinity, what that does is it divides the value of 1. So it has a dampening effect. And let me slide out a little here, and let's just go from -20 to 20 in the x direction. This dampening of the oscillation, basically the wave that goes up and down gets smaller and smaller and smaller as I go towards negative infinity or as I go towards positive infinity in the x directions. The question here is what is the value when x equals 0? Well, when I look at the graph, I don't really see anything all that great, but I know that x cannot equal 0. So if I hit trace and I plug in 0 for x, see that there's no y value. Again, if I hit the table of values, I have a value here and I have a value here for y, right? So I've got this when x equals 1 and when x equals -1. Now the clue is to look at this as it approaches 0. Now I'm going to do it in the table of values first. So what I want to do is I want to start at 0. And I want my table to be some ridiculously small increment, right? The change in the table. So now what I've done is, look at what I've done. When I hit the table of values, I'm going to start at 0, but what value does it look like it's approaching as I get closer and closer to 0? 1, right? What looks like, now the calculator is rounding. In fact, if I were to come into mode and change the float to like 9 decimals, I'm going to do this for the fun of it so you guys could see. Now if I look at the table of values, oh wow, it's going to round it pretty darn close to 1. So your calculator's rounding to 9 decimal places. But as I get further and further away, at some point we'll start to get like a 0.99 or something like that. But as you can see, the calculator rounds to 1 for quite some time. Okay? So it's going to be close to 1 for a while, and that's a rounding of the calculator. Now, what I want to do is I want to look at the graph and I want to look at the table of values. So what I need to do is I need to take the limit of the function as x approaches 0 from the positive direction. Okay? Then I also need to take the limit of the function as x approaches 0 from the negative direction. Okay? And I want to see if those two limits equal the same. If they do, then I can plug the hole possibly. And so that's what I want to look at. And I'm almost back to where I started, where I need to be. Well, actually, I went past it. So if I graph this, my function basically at y equals 1, I have an open hole right here. Right? And the function kind of does one of these things. Right? That's what my function looks like. And so what I want to do is I want to come in as close as I can from 0. So if I come in from negative infinity, right, what I'm going to do is I'm going to look at this graph, I'm going to follow the behavior of the graph and come as close as I can to x equals 0 from the more negative values from negative infinity. What that looks like on the table of values is I'm going to look at these y values as I get closer. See the decimals, how far they go out? 9, there's a whole bunch of 9s and it ends with a 4. Now it ends with 583. Now it ends with 733. Now 85. Now 9. See how it's getting closer and closer? If I could, what would you say x should be, or y should be, when x equals 0? If I could plug it in. 1. So as I come from negative infinity, as I come from this direction, my y value approaches 1. Now I'm going to do the same thing, but now I'm going to come from positive infinity. So as I come from positive infinity, I'm just going to follow the graph this way and look what the value should be. So I go a little bit to the left, and what is my numbers are doing the exact same thing they were before. As I get closer and closer to 0, my y value gets closer and closer to 1. Right?
Yeah.
Okay, so that should be 1. So I have the two-sided limit of the function as 1. Okay? I just need to plug the hole. How can I plug the hole? Well, what I need to do is I need to rewrite my function as f of x is equal to sine of x over x. Now, what do I write there? What is the domain that we're interested in there?
0.
I could say something like negative infinity to 0.
Oh.
Actually, I ran out of room. Let me rewrite that on another sheet of paper so you guys can see it a little clearer. I could say f of x is equal to sine of x over x when I go from negative infinity to 0. Union 0 to positive infinity. Now when I write it that way, am I including the 0 at all? No. Now here's the only thing I got to add. F of x equals 1 when x equals 0. So now what did I just write? What is this second line I just wrote on the paper? What does this represent? This
Fill in that little bubble. Except x can never equal 0.
well, that's why you have to, it's a piecewise function. I have to have two separate functions to let it work, right? To make it work.
So would you rather us write that whole like infinity?
This is all you need to write down.
Oh.
But I'm trying to teach you so you know too, right? So
Wait, why do you have to include the zeros? Because isn't it just negative infinity to infinity?
No, because it stops at 0.
it stops at 0.
X
Oh,
is
because
better.
it's discontinuous at the 1?
Well, it's discontinuous at x equals 0.
Oh.
So by plugging this in, I fill in the hole. Now it's a continuous function. Does that make sense?
Yeah.
Now, the reason Mr. Adams did the two one-sided limits, it has to have a two-sided limit in order for it to be a removable discontinuity. If I would have got 2 here and 1 here, I could have just given up. That's it, I'm done, I can't do it. It doesn't have a two-sided limit. The reason we do the one-sided limit is sometimes our discontinuity is at an endpoint, and we use a little bit different rules for endpoints. But clearly this is not an endpoint. Clearly it has a two-sided limit, right? Clearly the only thing I need to do is plug the hole. How do I plug the hole? When x equals 0, I'm going to make y equal 1. That's what we do in the real world sometimes. Sometimes in the real world, this function will model a behavior perfectly. Perfectly. But I cannot use x equals 0. Because I can't plug it into this equation. So if I were to write a program to model this and I wanted a continuous function, what I'd have to do is write the program this way. So that every y value is defined for every x value within the domain. It's in the programming language, it would be a little different, right? You use like some if-then statements. Does that make sense? All right, good. You're welcome. Any other questions?